but it's not really in the beginning. By the way, input, say it. Well, it's already over here. So they already graphed the 2 to the x power graph, which is review. And this is what I asked you to do on your test. Let me get that to where it kind of is here. So input 1, 2 to the first is 2. I input 2, 2 to the second is 4. You can see those points over on the graph. 2 to the third is 8. And then 2, oh, I know what I should have done. I forgot. I got to yeehaw this. My bad, dogs. Anyone? Thanks. Somebody's here. That's what I screwed up. What's anything to the 0 power? What's anything to the 0 power? 1. So 2 to the 0 is 1. And then -1, just to start seeing that asymptotic behavior. And that's the flip rule. So that's how that turns into a half. You see those points there. And then I told you in that section for exponentials, this could never be 0 as an output value. You can keep plugging in negatives. I'll just be annoying and put this above here. If I plugged in like -4, that'd be 2 to the 4th is 16, but then flip. That's still not 0, and that could never be 0. Even if I plugged in a -1,000,000, 2 to the -1,000,000 is 1 over 2 to the million, which is almost 0, but not quite. So what do humans do? They draw an asymptote to show that boundary behavior, that it's never going to get there. When I say inverse, you say switch X and Y. Tomorrow, are you guys coming tomorrow? Monday, we're actually going to graph logarithms, input, say it, output. But today, I'm just going to say, here's what a logarithm is. It's the inverse of an exponential. When I say inverse, you say switch X and Y. Boom shakalaka. 1/2, 1, 2, 4, 8. And then equal input intervals, -1, 0, 1. Remember that terminology? 2, 3. Remember we said these are equal input intervals going up by 1. Well, then we look at the y's of the first one, and the y's go up by a multiplier. Well, now for logarithms, I do want you to see this, because this is how you're supposed to analyze a chart to see if I have an exponential or a logarithm. The outputs go up by ×2. For a logarithm, the inputs go up by a multiplier, because it's an inverse relationship. All right, so just understand that. Understand that X means ×2. So maybe I'll put a dot instead of a, in case you're looking up, down, and kind of not catching all my words, so on and so forth. And then we're going to go ahead and graph this and see. You know what I should have done, though? I should have written this all in green. And in third hour, I will, because I'm going to graph this in green. All right. So not 0, 1, 1, 0. And then 2, 1. And then 3, 2, 3, 4, 2. Sorry, just struggling with my. And then 8, 5, 6, 7, 8. Who do we appreciate? 3. And then here's where it gets weird. Remember that the y's of the exponential could never be 0. That means the x's, shoots. I'm sorry. Yeah, the x, oh my goodness, that happens every day. The x's could never become 0. So I end up getting, let's see here. So what am I trying to do here? -1/2. Oh, I knew I did something wrong. That's a half. I was like, wait, what happened there? I just copied that number down wrong. So a half, -1. Remember that 1/16 value I got? 1/16, -4. All right, I'm actually going to graph that 2, 3, 4. The proof of this, or what I'm trying to prove, I guess, is that X couldn't, wrong, I wanted that in green, that the X's could never be 0. So I have another asymptote. That asymptote is actually vertical. This is really not behaving very well. So the green graph has a vertical asymptote because of the inversion of those y's. Those y's are now x's, and now that we have that that restriction there. Man, this is just awful. Something is going haywire on this. I can't function in this. I can't squeeze this and shrink. Great. It's always something new every day technologically. Trying to move me too. Nothing's working here. All right. I guess I'll have to use this scroller here. One thing I want you to write here is, and this is going to be written down in that box later. Say it. No. This is the, again, y equals x line. And we have symmetry. This point is symmetric with this point. This point is symmetric with this point, so on and so on and so on. So those relationships hold true. That's symmetry about the y equals x line. One more thing you should write for the exponential. This is a horizontal asymptote. That's y equals 0. For the logarithm, that's x equals 0 is the asymptote. All right. So the x-axis is y equals 0. The y-axis is x equals 0. It's almost an inverted relationship. Okay, I'll hide this real quick. And then I have to kind of write this stuff. This is mostly done already. That's why I wrote this in blue, and I'm going to write it in blue. All right, the graphs are reflections in the function y equals x because though they are inverses of each other. All right, we're going to make that connection here as we move forward. The domain of the exponential is the range of the logarithm. The domain of the exponential is the range of the logarithm. The range of the exponential is the domain of the logarithm. All right, so on and so on and so forth. And then logarithms and exponentials are called undue operations of each other, just like multiplication and division, right? That's what's true about them. And then therefore, what we're going to do at the end of the notes is do the f of g of f of test. All right. And that proves if I get x as a remainder or left over, then that proves two functions are inverses of each other. All right. I would like to try one more time to zoom in on this. Yay, it worked this time. Hallelujah, which is just a general word of praise not tied to any religion, right? All right. Public school. Okay. So now, how do I look at a chart of values and find out if it's exponential or logarithmic? This is kind of new to me too, but it makes total sense. Look at here. I have, and I'm going to write this too for terminology from the past. I have equal, let's put the equal sign there instead, equal input intervals. It goes up by 1. So it goes up by +1 as I go here. So I'm putting equal input intervals. And if you struggle from 1/3 to 1, skip it for a second. Go from 1 to 3, 3 to 9, 9 to 27. What's happening here? It's a multiplier. So whenever you have a multiplier, and then you could go backwards and say, okay, 1/3 to 1, that is also multiplying by 3. When the outputs are multiplied, then this is exponential. And this was an exponential test from our previous quiz/test from our last 2.1 to 2.8 unit. So that's not new. All right. All right. Now it says find the inverse of this. When I say inverse, you say switch x and y. I don't know why I keep doing that. I screwed myself up before. 1/3 is positive. I wanted to write negative. I don't know why. Then 1, 0, 3, 1, 9, 2, and then 27, 3. Hey, note to self, this graph now is a logarithm. This is a logarithmic graph. And on Monday, we'll input output when we graph a logarithm. I'm going to make you find 3 points, just like in an exponential, but that's what's going on there. All right, look at this next one. Hold on a minute. The x's, what's happening with the x's? What's the pattern? 3, 2, 1, go. Times 4. So when the inputs have a multiplier, or maybe you want to put a dot, times 4, over equal output values. Oh, look, this is a skip, but this one skipped. 4 times, actually, that is a mistake. This should be 3. 4 times 16 is 64. So that's a mistake in the charts. Change that to a 3, otherwise this would be bogus. All right, so the guy in the video didn't catch that. So these do go up by equal values on the right. and we do have to check that to make sure we have equal output values of +1. Otherwise, we couldn't make a determination if these weren't equal in their steps, I guess, to say. That means that's a logarithm because it's inverted. The relationship's inverted, switch X and Y kind of thing. All right, finding the inverse ain't no thing. Chicken, anyone? Wing, 0, 1, 1, 4, 2, 16. Yeah, definitely a mistake in the notes. That happens all the time. Certainly ain't going to judge as we use these notes from these people. Okay, now here's what goes in this blank. Okay, we're going to put y equals 2x here and prove something. Y equals 2 to the x. And then y equals log base 2 of x. And then actually we're going to prove that these are inverses of each other, but then we have to do something else. We got to do the f of g of and g of f of later. Okay, and then this actually happens later in our notes too, as I got to kind of get going here. How do I well, first of all, what's an inverse? When I say inverse, you say what? Switch x and y. And then honestly, this is what we're going to do. I do this. To solve for y, I just change this to a logarithm. That's the base, that's the answer, that's the exponent. So when I throw the word log in front of this, what happens? Who becomes the base, everyone? 3, 2, 1, go. 2. Who's the next thing? Is it x or y? It's x. And then this isolates the exponent y, and then we could see that we have that. So when I switch to x and y and then resolve for y, I got the other function. That proves that these are inverses. When I take this one, I'll do this in blue and I switch x and y because I got to speed this up a little bit. Well, when I take the word log away, then I have these 3 positions. And that's literally what I do. When I just get rid of that word, everything changes. Who's the base? 3, 2, 1, go. Who's the base? Oh, sorry. I see why you're pausing. I switch X and Y. I never changed that to Y. That's a whoopsie daisy. When I get rid of the word log, who's the base? 2. Who's the exponent? X. And then what's left over? Y. And then that is that. So that's showing that these two are inverses. And then so we would say yes there. So we will do this in our later ones here, determine if these are inverses, and I'll show you number 1 for sure. Okay, but now I wanted to do this. This is one thing for first hour I was short on, literally finding the inverse of this function. Okay, so we'll get to this. And then those are the end, right? Down at the bottom, right? I'll at least get to that number 1. Well, first of all, when I say inverse, you say what? Switch x and y. So the very first thing you do is x equals 3 times log base 5 of y. And I want to make that mistake again. I made that mistake in the last one. I still called that x. Now, he did something different on the thing. I like my way a little bit better because it's more direct. First thing, though, is what do I have to do? What do you think I have to do first mathematically? Divide by 3. I don't have 3 positions. I got that 3 floating out there. So I want that 3 divided. And then I am going to rewrite this here because it's really only one more step my way. But he does use a rule from whatever you do to one side, say it. And I might put his video on there. No one will watch it. But and I don't mind what he does, but I just always have done this. I now have a logarithm. I want to change it to an exponent. What's this called? The base. What's this called? Very important. No, that is the what? It's the whole purpose of a logarithm to isolate the exponent. So for those that were messing that up in the quiz is, if you know that's the base, you got to know the point of a logarithm. It's to isolate the exponent. So then what's left over? I called it the what? Answer, but then they called it the argument. I guess it is called the argument. So now I get rid of the word log. What's the base? Say it. 5. What's the exponent? X over 3. And then what's over here? Y. And then maybe what you might say is Okay, let's rename it the inverse of f of x. And it's just 5 raised to the x over 3. So there's another indication that I have a logarithm, and then the inverse of it, it's an exponential. And we can see that. Okay, one more, and then I'll do that f of g of f of thing. Of course, this is y, so I change it to x. Oh, this is so easy. And then this is 10 to the y over 6. Okay, I already have my 3 positions. What's this called, everyone? What's that called? The base. What's this called, everyone? The answer. Actually, I should have done that in reverse. What's this called? Obviously, the exponent, because I don't have a logarithm. So when I went over there, you might have said exponent. But no, that's if it's a logarithm. So this is the base. Ugh, that was B. This is the exponent. And then this is the argument or answer. We had a quizzes and they called that argument. And that's fine. When I put the word log in front of this, what happens? What's the base? 10. What's the what goes next? X. And then this equals y over 6. And then what's the last thing you have to do? Multiply by 6, and then we can write this in function notation. Yep, it's f of x, so it's the inverse of f of x. 6 log. This is really the way I do it. They do it by undo operations from a couple properties that we had yesterday, which is okay. It really hammers the properties down. We'll have to get back to those properties later. So I'm not going to do 2, but I am going to do this. Determine if these are inverses of each other. Here's what you have to do. You already have this typed in front of you. I know I'm going fast. And I didn't quite like how he did it. He kind of skipped some steps in the other video. So that's why I'm taking over. So how do I do f of g of x? F of g of x. I plug in. This is where the rules are going to come in from yesterday. And this might be fast. This is why I'm taping it. You might watch this last part again. So it's f of whatever g of x is. And then what's f of g of x? Wherever there's an x, I have to plug in this whole expression in there. So this becomes 5. I'm going to write that 5 really like big times 4 raised, and then replace x with this 4 log base 5 of x. Oh no. Well, what's 4 times 4? 16. So what I needed this to be was 1, because that was the rule. And actually I know what the answer is. What I'm supposed to get is x. This is screwing it up. If that was gone, then this is equal to x. Do you remember that from yesterday, that rule? 5 raised to the log base 5 of x equals does equal x. This does not equal x because of that 16. So guess what? Are these inverses or not? No. So you don't even need to do the other test if they're not inverses. But if that first one does work, then you do. All right. So we're going to be a little short on the notes here. Remember these rules when you're finding inverses. 10 raised to the log base 10 of x does equal x. And then that would be a proof that that happens. That 16 there actually screws things up. The reason I didn't tell you what actually the answer is because you're missing a rule and we haven't learned it yet. So a little bit different there. All right. I wish they had one that worked so we could see that rule actually in action, but it doesn't work out. I don't know why I erased that. So go ahead and look at that work there. Okay. Perfect timing. How do I get out of this video? I always do that to myself. Oh boy, here we go. Struggling. Oh, there it is. There it is.